Good morning, students.
Good morning, sir.
Good morning, sir.
Good morning,
Morning,
everyone.
sir.
Okay, so anyway, we have started late, so let's not waste time. So in the previous class, we discussed about, yeah,
Can you make everyone attendees, sir?
yes. Okay, so last class we were discussing about the hash function, the different types of what I can say, yeah. To produce an authenticator, we use three types of functions: hash function, message encryption, and message authentication code. We know what is message authentication code and the difference between hash function and message authentication code. Now we have to discuss something about message encryption. Okay, so that's what we discussed yesterday: message, hash function, and message authentication code. So we discovered that with the help of hash function, we can, and by doing digital signatures, we can actually address the authentication and integrity of any data. And we also discussed to some extent that how to actually go ahead with confidentiality. Okay, these three are the major aspects of security. So now, typical secure hash function. There are two slides. You can go through these slides by yourself, students, which is not really important with respect to the syllabus, but we have added it in the slide. Just go through by yourself once I share you these slides. Okay, these two slides. So directly I will move to the next slide. Basically, that is, say for example, when you sign up for an email address and password, generally what happens when you type your username and password? So password runs into a hashing algorithm and stores the hash of your password. Okay, so stores, basically when you give the password, the actual password will not go through your network to the server. Okay, so basically, yeah, it gets converted into hash value, and then so each time you log into your email, the email service hashes the password which is entered and then matches this hash to the database hash which is already collected. Okay, when you actually create your account, you might have given a password, and that password will be not stored as it is, as we discussed earlier. Since it is a it is a fixed password, it will not be stored as it is. It might be like salting or what we can say. What are the two things we did? A fixed password hashing and fixed password salting. So generally, in most of the server, in most of the email architecture, fixed password hash will be stored instead of the password itself. And whenever you enter the password, it generates the hash value of your password, and it tries to matches that with a already stored hash value. Is that clear? Only when it matches, it will allow you in. Okay, so this will actually avoid some an attack called as phishing attack. Phishing is basically somebody, instead of you logging into giving the password or taking your password in between source and destination. So that's how this is an example, like in normal mail architecture, how authentication is done. Okay, so digital signature needs what? A digital signature needs a shared key or a public key or private key or all of them. What is your answer, students? We know what's a digital signature now. Any guess?
Public key system, sir.
Public key. Are
All of
you sure? See, let me again write it down. Okay, you will see that in the upcoming slides again. But keep this in mind. Whether what I'm not going to give you the answer. Okay, what keys do you require for digital signatures? Do you need private key? Do you need shared key? Do you need public key? Or all of them do you need? Okay, just think about it. Keep this in mind. I will answer this to you after some time after discussing digital signatures. The upcoming thing is digital signature. We'll be discussing about that. Okay. Encryption and decryption provide secrecy or confidentiality, but not what? This is again another question. Encryption and decryption provide secrecy or confidentiality, which we generally call. But encryption and decryption doesn't provide what? Does encryption and decryption provide authentication, integrity, and privacy? All the three, or which one it will provide? So again, this also you have to keep in mind and answer me later once we discuss couple of slides, upcoming slides. Okay, digital signatures. So properties, what are the properties of digital signature? Message authentication protects two parties who exchange messages from any third party. Okay, so basically the property of digital signature is to protect two parties who exchange messages from any third party. Okay, it is very much and now I am talking to you. I'm very sure that you are only logged in, thinking that you have not given your username and password of team software to someone else. Okay, assuming that. So it is a authentication, mutual authentication what we have. Okay, similarly digital signatures will protect two parties who are exchanging messages from a third party. Third party may be generally a intruder. However, it does not protect the two parties against each other. Okay, however, it doesn't protect two parties against each other. Keep this in mind. Okay, so how does it work? You can see here the diagram. You have a message, and message is actually encrypted using what? So this is a diagram. Okay, message authentication and confidentiality. Authentication tied to plain text. Okay, so what happens here? You have a message. You are feeding the message into uh, uh, a compressor. Okay, I think there is some issue with this diagram. Okay, students, just neglect this diagram. I will add another diagram, a different diagram, which I told you in the previous class, to the in this space, and I will help you out with that. This diagram is not quite clear. Okay, let me not discuss about this diagram. So mechanism for non-repudiation, the basic idea is use private key on the message to generate a piece of information that can be generated only by yourself. Okay, because you are the only person who knows your private key. We have already discussed all these things. Public key can be used to verify a signature. So everybody can verify, anybody can get your public key. Generally signatures are created and verified over the hash of a message. Okay, why? Generally signatures are created and verified over the hash of the message. Can anyone tell? Yesterday I told you. So let me draw it again to help you out with the I have A, B. Okay, so I have a message to send to B. So what I have M, and this message is given to a hash function, and you have h of m. Is that clear? You have a hash code of the message, and this hash code of the message is encrypted using private key. Okay, using private key. Is that clear? What is the other notation for private key, students? Yesterday I told you. Do you remember? I can also write it as
KS minus. KS minus.
So it is K sender minus. Okay, so this is clear that you have the hash code of the message and you are encrypting it using the private key of the sender, which is called as digital signature. So now can you tell me what keys we need for digital signature? Do we need session key here? Do we need shared key here? Yes or no? Did I use any shared key, students, here for creating the digital signature?
No, no sir.
No, no. So shared key is not required. Did I use any public key here?
No sir.
Public key is also not required. So what I have used is only the private key of sender. So your answer for this question, digital signature needs a private key system. Is that clear? It needs a private key system. Answer for this question. Okay, so what I did, I have the message, I took the hash code of the message, and then I have encrypted that hash code using the digital, using the private key of the sender, which is called as digital signature. So this digital signature, okay, this is digital signature. So when I send a message, if I send digital signature plus message, I am going to do the digital signature. This is DS, not OS. Okay, this is DS. Digital signature plus message. I am sending it to B. So upon receiving this B, what will B do? B have the message as it is. Okay, fine. Then what will B do? B will try to decrypt it. How it will decrypt this digital signature? That means this H of M is encrypted using the private key of the sender. So it will have the public key of the sender. From that it will decrypt. So it will receive H of M. So this B will receive H of M plus M. Okay. So this H of M, now it is very much sure that it is sent from A. Why? Because you can decrypt this H of M only using the public key of the sender. So authentication is proved here. Okay. Now question what we have here is, generally signatures are created and verified over the hash of the message. Why? Very simple question, students. Can anyone tell? We could have simply encrypted the whole message using the private key of the sender, right? But we didn't do that. We actually encrypted only the hash function of the message using the private key of the sender. What might be the reason? To prove what you are going to do that?
Sir, because anybody having the public key can decrypt the message, no sir.
Okay, that is one reason. Any other reason?
To prove integrity.
Yes, very important point, to prove integrity. How integrity is proved here? See, if any data is altered in this M, if any data is altered in this M, say for example, M is equal to X, Y, and Z. Okay, XYZ. That means message is XYZ. You are sending XYZ plus hash code of that XYZ. If in transit, if this message is altered, so what happens when you try to find the hash function? I mean, when B try to find the hash function of this message, instead of XYZ, if it is YZX, that means message is altered. So the hash function will vary. Hash function that is generated in B and hash function which is received will vary. Once it is varying, that means integrity is not proved there. Is that clear? So that's why generally signatures are created and verified over the hash of the message to verify the integrity of the message. Is it clear, students? This question, very important question. Is it clear to you?
Yes sir.
Okay. So
Sir,
yeah.
sir, before you told private digital signature needs private key, but
Yes.
that is only for the encryption part. Uh, the point is we have to decrypt also, no, sir. So
Yes.
that is done using the public key.
Yes.
So it needs both, right? Actually,
Who needs
public
both?
key and private key.
See, I am a user. You are also a user. I will have my own private and public key. You will have your own private and public key. And I can also easily know your public key. You can also easily know my public key. If I encrypt something from my private key, you can easily decrypt it because you have you have my public key also. Is that clear? But if I encrypt something using your public key, who can decrypt it? If I encrypt something using your public key, who can decrypt it?
Only I can decrypt it.
Only you can decrypt it. That's the analogy. That's the funda of public and private key pair. Now, what sender is doing? Sender is encrypting the hash code using its private key. And when it is received by the receiver, what receiver will think? Okay, A has used A's private key. So who is having private key of A? Only A have the private key of A. That means it is very sure for B that A has sent that message. It is very clear. Authentication is proved there. Is that clear? And when B decrypts that message using the A's public key, what it will get? It will get H of M. And B also have its message, actual message. So that message is fed into another hashing algorithm, same hashing algorithm. So B will also get a hash code, and the received hash code and generated hash code will be compared with each other. And if they are same, integrity is also. Am I clear?
Yes, sir. Yes.
Sir,
Yeah.
I had a doubt. Like, sir, the options said basically public key system and private key system, sir. Like, private
Yeah.
key system is basically symmetric key encryption, no? So symmetric key cryptography, like private public key system. I mean, private key system.
It
The
is not actually basically system. Forget about that word system. What keys you need? That's the question. What keys you need? That's the system. So basically, it is private key what we need for generating a digital signature.
yes, sir.
Got it? I will remove it. That system word I will remove it.
Yes, sir. Yes.
Okay. Any other questions, students?
Sir, is
Regarding
hash function known to everyone, sir? Like, just like public key.
no, only if you share it will get other person will get to know. Public key can be known to everyone with the help of directory services. See, there will be something called as directory services. You might have seen the what I can say, if you have a landline connection long ago, like you used to get a yellow pages book, a directory where you have all the phone numbers, the what I can say, phone number, the landline numbers which are there in the particular district or state. Okay, like that in internet also you will have directory services, and those directory services will have the public keys of all the users in your ISP. So if you want to get the public key of anyone, you can easily go and there get it. But like that, there is no repository for hash function. Hash function is only for that particular session. Okay, whereas public keys is a permanent thing, permanent in the sense for some time. Is that clear? Hash function is not of that type. So you yeah, I don't know hash function what you have generated unless and until you send it to me, whereas I know your public key. I need not you, I don't want you to send it to me. Is that clear? I know your public, I can get it.
Yes, sir. Because I asked because if we know the hash function, suppose let us say a person C can decrypt the message and he himself can write his own message and again use that hash function to generate another key and again send it to B. So
Yes.
B, B cannot ensure that A only has sent that message.
Yeah, but again, B will ensure, right, when A has sent the message, because B requires, B will get when some C tries to encrypt the data and send it to B. C will encrypt using the C's private key. C cannot encrypt the data using A's private key, no? Because your hash function is already encrypted using A's private key.
Yes, sir. I told like we can replace that hash function, so that's what I told.
You cannot replace. When you want to replace, you have to, like, whatever that is encrypted, that hash function, this part, the encrypted hash function, you cannot replace. If you want to replace, you have to decrypt it and replace. And again, see, replacing is what you cannot replace the digital signature. Okay, you are telling you can only remove the content, that is h of m, and add another content h of m into that. You cannot do that basically in a digital signature. That's not possible.
Yes, sir.
Got it?
Sir,
Got it, sir.
Yeah.
you said to ensure integrity, we are encrypting only the hash code and not hash code along with the message.
Yes.
Yes, miss. So why that's integrity? We can check even when the message is encrypted, no, sir? How is that making a difference?
You see, if somebody looks into your message, see, when you get the hash code of the complete message, it is just a code, no? Can you repeat your question?
Yes, putting it in a simple way, I'm asking why we are not encrypting the hash code along with why we are not encrypting hash code along with the message for the digital signature.
Because that will create a very big digital signature. Okay, hash code plus message, if you do, that's a big data, right? It's a huge data. When you are creating that's not the actual procedure for. See, this we are doing only for the purpose of authentication and integrity, and for proving confidentiality we do something else. Okay, I will discuss that in the upcoming slides. I will discuss, then you will understand why we are not encrypting the whole message with your private key.
Yes, sir, I understood. Sir, initially you asked something and Sahana replied that integrity. Uh, can you just
Yeah,
repeat that point?
yeah, see, the question is why hash it, why not instead of complete message, why not instead of directly encrypting the whole message with private key, why you are encrypting only the hash code with the only the hash code you are encrypting with a private key? There are two reasons. One is to prove integrity. Other one, if you just encrypt the whole message using the private key, what happens? Anybody can decrypt that message, no? You are not proving any confidentiality there. Anybody can decrypt it. Do you agree?
Yes, sir.
These are the two reasons. One is, the main reason is why hash code of the message is encrypted, because to prove integrity. The other one is, if why not, the question is if I have another question, like why not the whole message is encrypted using the private key? If you encrypt the whole message with private key and send it, anybody can decrypt it, because anyone can get the public key of your any user. Okay, so anybody can decrypt it. You are not proving any confidentiality is there. So for proving confidentiality, we will do something else. Okay, we will see how we are going to prove confidentiality later. Now we are only concerned about authentication and integrity in this part of study. Okay, so if you know how to, like, how integrity and authentication is proved using hash function, digital signatures, that is good enough.
Okay, sir.
Got it? Did I answer your question?
Yes, sir.
Okay, let's move to the next slide. So yeah, this is one good diagram. See, generic model of digital signature process. You have, okay, this is this diagram I wanted to replace there. Anyway, you have a message. You can see here, this is the message, and a message is actually encrypted. Digital signature generation algorithm. A message M is fed into okay, here see students, in this diagram again you are only seeing the authentication process, you are not seeing the integrity process here. If you see, there was a question previously, generally signatures are created and verified over the hash of the message. Reason is it provides integrity also. If you don't do that, if you directly encrypt the message, you can see here you have the message digital signature generation algorithm, and for that you are giving message and Bob's private key as input. You have received the Bob's signature. Is that clear? So you are not taking the hash code of the message. In this case, you cannot prove the integrity. Is that clear? You cannot prove the integrity. See, there is a digital signature generation algorithm. You are giving message and private key as input. You have created the digital signature. You are appending that with the message. You are sending it. And what happens? The message is received, and that message is fed into the digital signature verification algorithm and the signature also. Alice will decrypt it using the public key. Is that clear? Bob's public key you can see here. So basically you are proving the authentication. Here you are not proving the integrity, but instead directly giving the message. If you take the hash code of the message, give it as input for the digital signature module, then get the digital signature, then append it with the message, you can easily prove both authentication and integrity. Is that clear? But here there is no point of confidentiality. Confidentiality doesn't come into picture here. That's what I want to make it clear to you. Okay. So simplified decryption. This diagram. Okay. I will remove this diagram, which is not required to you students. So the what I said you before, but I have a other diagram which I will send it to you. You can see here you have a message, put it into the hash function, you get the hash code, and then encrypt it using the Bob's private key. So this is what I told you. This will provide both confidentiality and integrity. Sorry, authentication and integrity. Is that clear? It is not providing any confidentiality. This is what I told you initially. You have a message, take the hash code of the message, and then that hash code is encrypted using Bob's private key and send it to the sender. And what happened upon receiving this, receiving that uh, uh, digital signature plus message, that message is again fed into the hash code. You will get a hash, and then when you decrypt that digital signature, you will get the hash code, and both will be compared. And when both are same, you are proving integrity here. Here you are proving authentication. Both authentication and integrity is proved. This is the diagram which proves. I will add a heading here later when before I share it to you. So it is for both authentication and integrity, and the previous diagram is only for authentication. Is that clear? So please analyze the diagram clearly. The first diagram is only for authentication, and second diagram is for both authentication and integrity proof. Is it clear, students?
Yes, sir.
Okay. I think these diagrams are clear. I thought it's a different diagram. These diagrams are clear. So I will share the same diagram with you. Okay. Okay. Then properties of digital signature. It must verify the author and the date and time of the signature. It must authenticate the contents of the time of signature. It must be verifiable by third parties to resolve disputes. Okay. Thus, the digital signature function includes the authentication function. So, what might be the attacks? Shown in the order of increasing severity. You can see there is a user A sending some data. Okay, and there is another attacker called C. So if C only knows A's public key, we can consider it as key only attack. Okay. Generally, it is not considered as an attack because it's easily you can know get to know the public key of any user. You can just contact directory services, inform them that you are sending some data to A, you will get to know the public key. You can easily do it. But if C is given access to a set of messages and their signatures, okay, with respect to A, then we call it as a message attack, known message attack. If C chooses a list of messages before attempting to break A's signature scheme, independent of A's public key, C then obtains from A valid signatures for the chosen message. It is called as generic chosen message attack. Here only specific messages are attacked. Okay, generic chosen message attack. Then the fourth one is directed chosen message attack, similar to the generic attack, except that the list of messages to be signed by chosen after C knows A's public key, but before any signature are sealed. Is that clear? So, okay, this is direct chosen message attack, and the last one is adaptive chosen message attack. C may request from A signature of message that depend on previously obtained messages signature base. Is that clear? So these are these are not considered as specific attacks with respect to a particular scenario we are speaking. These are attacks. See, it is not considered as the major attacks like eavesdropping, brute force, phishing, then snooping. All these are different types of attacks where which are considered as general attacks. So these are not those type of attacks. These are specific to a particular scenario. When A is sending data to B, what does he can do? Is that clear? So these are very specific again. So just go through these slides, which you can just go through again. You will easily understand this. Next thing, okay, there are four more types of attacks. Total break. C determines A's private key. Very important. When C gets to know the A's private key, C can do anything in the name of A. Is that clear? That we call it as total break. C finds an efficient signing algorithm that provides an equivalent way of constructing signatures on arbitrary message, universal forgery. Is that clear? C forges a signature for a particular message chosen by C. It is selective forgery. Specifically, you are forging a message. Then C forges a signature for at least one message. C has no control over the message. It is extensional forgery. Again, these four are different types of attacks. So the previously you have 5 different types of attacks. These are shown in order of increasing severity. The second slide of these attacks are more severe. Okay, so these are some of the attacks with respect to digital signatures. So what are the requirements of digital signatures? Must be a bit pattern that depends on the message being signed, must use some information unique to the sender to prevent both forgery and denial. It must be relatively easy to produce, recognize, and verify the digital signature. These are some properties or requirements of digital signature. Okay, it must be computationally infeasible to force a digital signature, either by constructing a new message for an existing digital signature or by constructing a fraudulent digital signature for given message. It must be practical to retain a copy of digital signature in storage. All these are the requirements for digital signatures. These things, students, there is nothing to explain here. You have to just keep this in mind, read it 2-3 times. This has to be there in your mind. Okay, so yes, we will stop here for the day. This next topics, recalling primitive roots, these are not required for your syllabus. So I'll be removing this from the slides, and then we will directly go to the Kerberos authentication service. Okay, which is very important, which is a application of authentication. So that we are going to study in the next class. So we'll stop here for the day. Take care, students. Any questions do you have? Okay, hope you don't have any questions. So you can leave for the day, students. Thank you.